And then the final talk of today is by James Hensman. He's a researcher at Microsoft Research, who are one of the partners, project partners for the Hub. And he's going to be talking on a probabilistic view of the LLM residual stream.
Thanks, Paul. Hi, thanks for staying all the way to the end and listening to my talk. So I've been working in machine learning for about 10 years. And I've worked with several of the people in this room, actually. I've worked on Markov chain Monte Carlo methods with Chris, and I've worked on Gaussian processes with Zubin. He referenced that this morning. I've worked on additive models. I've worked on lots of parts of machine learning that are at the intersection of just where statistics kind of bleeds over into machine learning. So I'm a big fan of how do we do computation in large statistical models and things like online learning, variational inference. And a few years ago, I joined Microsoft Research, and one of the reasons I wanted to join was this was really just the start of what is currently the AI boom. Microsoft is shifting heavily towards AI in all of its products. You will see AI in your Teams product, you'll see AI in your Microsoft Word product, you'll see AI like in a panel on your Internet Explorer window. AI is going to be everywhere. And I figured this was a really exciting thing for me to come along and work on. And what does a sort of statistical guy do in AI? I guess that's what the whole purpose of this theme is, right? Probabilistic AI. What do people like us do what do we do in AI? And so I wanted to tell you a little bit about some of the work that we've been doing, and I wanted to paint you a little bit of a picture of how computation happens in AI. And I think computation might be the thing that binds us all together right across statistics and Markov chain Monte Carlo and variational inference and Bayesian deep learning and so on. Computation is kind of at the core of it. And if I think about sort of progress that we've made in the last 10 years, you know, where we are in AI and machine learning is a result of thousands of people doing, you know, cumulative work, building on each other's work and making progress. But there are some inflection points, and I think those inflection points are largely to do with computation. So the first inflection point that I can kind of remember witnessing or being part of is I was at the NeurIPS conference in 2013, I want to say, and I was running a workshop with a guy called Joaquin Candela, and Joaquin worked at Facebook. And he was doing some stuff, optimizing ads, and I thought this was not particularly interesting. But he said, come to our event this evening, because there's a big thing happening. I said, ads? Facebook? Not really my thing. But he was absolutely insistent. I went along, and there was a room about this size, and Mark Zuckerberg stands at the front of the room, and he says, I want to announce the start of Facebook AI research. And from then, Facebook, or now Meta, invested huge amounts of money in computation, in massive computers that compute these huge neural networks that predict what word comes next. And another inflection point that I would like to claim is also to do with computation is a paper which came out in 2017, which is called Attention is All You Need. Has everybody read Attention is All You Need? Of course you have, right? I don't know if you were there at the NeurIPS event, but you could not get in the room when this paper was being presented because it was a massive, massive jump in performance for all kinds of NLP-like tasks. And what does this attention thing give you? What is so different about attention as opposed to what we were doing before this paper? I think it's computation. Attention allows you to compute things in a way that's parallel, whereas before we were doing things in sequence. We were running recurrent neural networks that predicted one word from the next, and we had a Markov structure. And that doesn't fit in our compute hardware very nicely, but attention allows you to compute things for all tokens at once, one big forward-backward pass of one gigantic neural network. And this fits beautifully on our compute devices. So I want to talk about computation, and I want to paint you a little picture of an aspect of what's happening inside these neural networks that maybe will be a different picture to the one that some of you are familiar with. So here's how these big ChatGPT-like models work, right? We give them a sentence and they continue the sentence on. Sometimes that sentence can involve special words that are the beginning or end of a message, or they might be the start of the reply to a message or something. But at its core, it's an autoregressive model that says what comes next. So when you type into ChatGPT, the capital of France is, what does it do? Well, the first thing that we do is we tokenize the input. Okay, so this will be familiar to lots of you, but if you don't know what tokenization is, it means just breaking up strings into little chunks. And this is the first place that maybe people who are good at computation and statistics might start thinking, we have something to add here. Because the way that we currently tokenize text is based on a method called byte pair coding, i.e. things that are really frequent, we give them a special token. So you can see in my really trivial example here, the word the has its own token, and capital with a space at the beginning has its own token. But in my completely fictitious byte pair coding scheme, capital F and the rest of the word France have represented by 2 different tokens. Okay, so we tokenize what's happening. What does it really mean? Well, every chunk of text gets given an integer. That's it. And we can map from sequence of integers back to text, or from text to a sequence of integers. That's what the tokenizer will do for you. And then the interesting bit, like how do we start computing with these integers? Well, we put them in a continuous space. So there is a big matrix called the embedding matrix. And the size of the embedding matrix is number of tokens that we have available to work with by what I'm going to call the hidden dimension of the neural net. Okay. So we take these integers and we index this embedding matrix, and we take the rows out that correspond to the words that we've seen. We might do a little bit of modification of this embedding matrix to represent what position they've occurred in. I'm not particularly interested in that today. So each gray dot on my figure over here is one row of my fictitious embedding matrix. And obviously, I'm doing things in 2D to show you some pictures. And each of the highlighted points corresponds to one of the tokens that's in the sequence. And we're going to compute what token comes next. So how does this computation happen? Well, we use a big neural network to process these tokens. So we saw a really lovely first talk this morning about how neural networks look an awful lot like solving an ODE because of the residual connections. I completely subscribe to that view. I think that's absolutely the right way to think about what is happening when we process the information with a neural net. But I want to go a little bit deeper and say, well, what's happening in each of the components here? And I'm going to claim that there are actually 3 interesting blocks in your transformer neural network. Most people will say 2, but I think the missing secret key ingredient of the transformer networks is actually the normalization layer. And I think there's all kinds of interesting stuff, and I'm going to show you some really cool stuff that we can do by just considering what happens with the normalization layer. So here's a picture that you'll see in many deep learning papers. It should look familiar to many of you. We have an attention block and a feed-forward network block, and we have residual connections going around these blocks. I hope it's clear what this diagram is implying. But there's an extra block here, which I've written as x over abs of x, and it's the normalization block. So what we're going to do is we're going to take our new representation of the input sentence, and we're going to process it with this transformer structure, and we're going to apply many layers, so many transformations of this thing. And I want to talk first about what happens in this normalization block. So the most common normalization operation that you will see is called layer norm, which is a terrible name for this operation. So what it does is it takes your vector representation of your token, and it computes the mean and subtracts that, and computes the standard deviation and divides by that, and then it does some linear rescaling. There's a lovely tutorial paper on these constructions written by Rich Turner, and he says it shouldn't be called layer norm at all. It should absolutely be called token norm, because what we're really doing is just taking each of these representations individually and pushing them back to the unit sphere. Okay, so don't think about the rows of the matrix as being some random variable. Just think about them as being a vector. And the operation that we do when we do layer norm, or so-called RMS norm, which is a variant, is really to just divide by the length of the vector. That's it. So everything is now kind of moved to the unit circle. What do we do next? Well, we apply attention. Conventionally, attention is the first block that we apply. I'm not sure that that's a particularly well thought out convention. I haven't seen a good thorough exploration of whether we should apply attention first, but this is the convention. And what attention does is say, perturb each representation of each token according to its relative position with every other token. Okay. There's a bunch of keys, queries, and values and computations in there, but that's not what I want to focus on. What I want to say is each particle, each position is updated according to how it is positioned relative to all of the other representations of the tokens. So we do this and we add in the residual connection, and as has been pointed out, this looks an awful lot like taking one Euler step in an ordinary differential equation. Okay, and then the next block is, which I haven't highlighted, but the next block is we map everything back to the sphere. Okay, we apply another normalization block. And then we have another type of block, which is sometimes called the feed-forward network, or FFN block. And this is what most people would recognize as a standard neural network in some way. So classically, this would be, I perform a linear matrix operation, and then I have an element-wise, say, GLU operation or similar, and then another linear operation. There are also variants now that include gating operations and so on, but again, the precise details of that I'm not too worried about. But there's something here which applies to each of the token positions independently. Not according to their relative position, but you can just think about this as a field which just pushes all of the particles in some direction in a nonlinear way. So we compute these updates next. And then what do? Well, we go back around the loop and we do it again, and we do it another 30, 60, 100 times, depending on the depth of your neural network. So in a fairly large open source neural network, it's about 100 layers deep. In a fairly small one, it'll be maybe 16 or 24 layers deep. And what we get to at the end is some way of predicting the next token. So you can see here the last token in my sequence is the blue one. And now that I've processed it with this neural network, I'm going to predict the next token by seeing how close it is to some new set of tokens, so new set of embeddings. And OK, this now blue has been processed. It is now close to this red one, which is the Paris token. And we got the answer that we came for. So this computational system, for me, yes, absolutely looks like solving a differential equation, but it also looks an awful lot like some kind of particle system where we have particles pushing each other depending on their relative distance. It also looks like the whole thing is a differential equation which is restricted to the unit sphere, because every time we do an operation, we map the result back to the unit sphere. If you were to solve an ordinary differential equation using an Euler method and you knew it was restricted to the sphere, this might be the first thing you tried. Right? You might try taking a linear step and then mapping back to the unit sphere if you knew that's where the solution lay. OK, so what? This is the one theorem that sort of powers the two papers that I'm going to show you in a second. And it's really, really simple. It just says, it doesn't matter what the orientation of the sphere is. In other words, I could just spin around all of the embeddings at the beginning of the neural network and spin around all of the forces that are applied to the tokens as we go through the neural network, and I could come up with an completely equivalent set of computations just in a rotated coordinate system. Maybe that's not particularly surprising because we know that everything is kind of stuck on the unit sphere. But here's another nice thing you can do. We can easily compute this new neural network in the coordinate system. So you give me a trained large language model or small language model or vision model for that matter, anything that has this transformer construction, and you tell me, I want things to be oriented like this, please. So you give me a rotation matrix, Q, or a reflection matrix, some kind of orthogonal matrix that tells me how you want things to be oriented, and I can modify the large language model by multiplying all of the weights in it by your matrix Q, and I can give you back another large language model that computes exactly the same output, but all of the intermediate computations have been moved around by Q. So here's how it works. We take each of the weight matrices that appeared in your attention block or your feed-forward network block, and identify some of them as being input weight matrices and some of them as output weight matrices. So whether they're on the left-hand side or the right-hand side of the block. And I'm going to multiply them by Q on either side. And my claim is that these Qs will cancel out. Okay. So everybody knows that, okay, if you have an orthogonal matrix, Q times Q transpose is the identity. But the special bit of the theorem is really that the rotation matrix commutes with our normalization back to the sphere. That's what makes this thing work. So in other words, if I rotate the orientations of my computation, and then I renormalize it to the sphere, well, I could do those two operations in the other order. I could move to the sphere and then rotate, or I could rotate and then move back to the sphere, because rotating doesn't change the norm of the vector, and removing the norm of the vector doesn't change the rotation. So these two operations will commute. So this is a really useful theorem, and it allows us to do some computational things that I think most people in this room will find really familiar. And the first one is called principal component analysis. Everybody here knows about principal component analysis, right? We all studied it as, statistics 101. So here is a paper that we wrote that says, well, now that we have this theorem that says we can modify neural networks using orthogonal matrices, I can do principal component analysis sort of inside these neural nets. And by this, I don't mean I'm going to compute the activations and then compute SVD on the activations. I mean, I'm going to bake in the principal component transformations. So here's how it looks. So here on the left-hand side is a schematic of what happens. This is going upwards this time, which is a different convention in deep learning. But there's an attention block at the bottom and a feed-forward network block at the top. And I've modified the input weights by multiplying them on the left by Q, and the output weights by multiplying them on the right by Q, or Q transposed. And then what we do in principal component analysis is we take our data set and we rotate it, and then we throw away the small principal components, the small singular values, right? Well, the equivalent of that here is to delete parts of the network. So if you think about trying to delete some of the singular values that are in the information being passed between the blocks, well, that's the same as deleting the rows or column of the weight matrix that process those activations. So what I'm showing you in the shaded region on the diagram is, we can now cut off the last so many columns of the weight matrix, and that will remove the smallest singular values. Why would you want to do this? Computation. So what I'm showing you on the right-hand side here is for 4 different medium to large language models, how much computation can we get away with removing? So the first 3 language models are Meta's Llama 2 models, which is sort of pretty much the state-of-the-art large language models that are open source and available to everybody in here to play with. And they have 7, 13, or 70 billion parameters. yes, you need multiple GPU devices just to load these models up. You need hundreds of thousands of pounds of hardware just to load the largest model. And what I'm showing you in the plot here is the performance in terms of downstream accuracy on language modeling tasks as a function of how much of the network I can cut away with PCA. So you can see that for the largest model, I can actually remove 25% of the model and lose about 1% of the performance. So I can give you a 75% of 70 billion model, which is very close to being as good as your 70 billion model. And that, okay, that's for a small drop in accuracy, how well we can predict the next token, we can actually get a huge saving in the compute. Okay, what else can I do with computational invariance? So removing parameters is one really good way to make your AI computation a little bit cheaper. But the prevailing way is actually not to remove parameters, it's to reduce the bit width. So I guess when you open your R console or your Python window or whatever, by default, all of your floating point numbers are going to get stored in 64-bit precision. Okay, and that's kind of the standard. And if you're really finicky about what you're computing, you might even go for 128-bit precision. But all of these bits are kind of expensive. And what we would like to do is reduce the number of bits that we use to store the weights of our neural network and to store the activations that are flowing through our neural network as well. So the standard in AI computation now is to use half precision, i.e. to use 16 bits to represent every weight and every activation in a neural net. The first time I learned about this, I was pretty frightened. Like we're throwing away most of the bits, like all of my lovely, I never used to worry about my floating point precision, right? It would just kind of work. Occasionally my Cholesky algorithm would fall over, and then, okay, I would pick it up by adding a little bit of diagonal term, right? But now everything is computed in half precision, but even half precision is far too much. Even half precision is super wasteful. So what we're doing in this method that we call CARROT, which stands for quantization with rotations, is saying we can use this computational invariance trick to make the distribution of the stuff that's happening inside the large language model more amenable to low bit width representations. And that's what my figure is trying to show you. So on the left-hand side here, I am showing you a plot of the distribution of one of the activations, one of the computations that happens inside Meta's Llama 2 language model, 70 billion, somewhere deep in the network. I think it's in the 10th layer. And so what the plot is showing is these vectors are 4,096 dimensional, so that the horizontal axis is the index of the vector, and the vertical axis represents the magnitude of what we need to store. And the different colors here are showing you the sort of range of the values that we see empirically when I pass a few hundred sequences through the network. And what you notice is that there are some dimensions or channels or features, they're sometimes called in deep learning, which behave kind of nicely, right? They just have a little sort of Gaussian-ish distribution. And there are some that do not, and there are some that sort of spike horribly. And these big spikes are really bad news for low bit width representations. So the way that a floating point number works is that we have some bits that store like a linear scaling and some bits that store a logarithmic scaling. And if you have spiky behavior in the things that you want to store, then you're going to need more bits in that logarithmic scaling part, or the exponent part of your representation. So what we can do with computational invariance is say, hey, let's find a different orientation of the neural network that doesn't have this spiking behavior in it. And so that the marginal distribution of the vector that I need to represent is now much better behaved, and I can quantize it, or I can represent it with a far smaller number of bits. One thing that you could do is just choose a random orientation. That makes some of the spikes go away, but you can do a little bit better than that, in fact, by using a Fourier method. So you can choose a rotation matrix Q, which is actually just an FFT transform. And then your computation is also nice and cheap. So what does it mean to reduce the bit width? Well, computationally, it looks something like what's happening on the right-hand side over here. So in blue is the number of milliseconds that takes for my relatively small GPU accelerators to compute one of the matrix multiplications associated with this really big neural network. And blue is in half precision. And then red and yellow are with 4-bit integer-only precision. And you can see that the relative speedup is pretty close to 4x. And for the really big model, it's better than 4x. So the amount of computational milliseconds we need to compute reduced by a factor of 4. And on the left-hand side, what I'm showing you is the benchmark numbers for how we measure how much degradation we have in performance. So the standard that we use here is to compute the so-called perplexity, or the loss, basically, on some fixed data set that everybody has agreed is reasonably representative. So the so-called Wikitext to perplexity test. And lower is better. And you can see that our method, Carrot, in combination with some other state-of-the-art method called GPTQ, actually gives you only a very small number of bits in the increase in perplexity, even though the computation is reduced by a factor of 4. Okay, this is the point where I should say thanks so much to my co-authors. So we wrote these 2 papers. One of them will be in iClear. The other one is on arXiv now, ready for your feedback. We'd love to hear from you. Some of the co-authors I have here are interns who are some of your PhD students who came to work with us for a summer, and some of them are postdocs. Microsoft Research has a postdoc program. So please do encourage your students and your graduating students to come and work with me and my colleagues at Microsoft Research in some of these application areas. And that's all I wanted to say. Thank you so much.
So maybe we'll just have a couple of questions. First of all, I've got one from the virtual audience.
Okay.
So I'll ask that out, and then people can put their hand up if they want to ask James a question. So this says, in slice GBT, is removing small singular values equivalent to Marchenko-Pasteur denoising?
Equivalent to what denoising?
Marchenko-Pasteur.
I have absolutely no idea. You'll have to send me an email, and I'll answer with more detail when I've had a chance to look up what that is. But it is completely equivalent to principal component analysis. So if you're familiar with doing SVD, then this is what we're doing.
Any other
Masha's got a question.
I can yell if you want me to. That's enough. About slice GPT as well, you report on the difference in mean error depending on the reduction of the number of parameters. Do statistics other than the mean not matter?
So what's going on when we say mean error is, it turns out that evaluating how good your large language model is kind of tricky. So in the table that I showed you at the end, we were looking at perplexity, which is effectively the model's loss, but that's actually really not very representative at all of what happens downstream when somebody actually uses the neural network. So some kind people have set up a suite of benchmarks that try to quantify how well your language model is doing. And there are a bunch of tasks in this. So one of the tasks might be solve a little mathematical problem. Another task might be a multiple choice question. Another task might be write a summarization of this document for me, and so on. And each of these tasks is some kind of score out of 100. And what I'm plotting for you here is rather horribly just the mean across all of the tasks that we selected.
Okay, we could have one final question if there is.
Thanks, a very good presentation. There are people experimenting with getting rid of layers inside the network. Have you looked into this as well? Can you also combine this and see if you can get rid of some of the layers in the middle of the network?
Yeah, so the question is, can we get rid of some of the layers in the middle of the network? I have not tried getting rid of some of the layers in the middle of the network, but several other people have. I'm aware of at least 2 papers that have tried to prune out entire layers from what's happening. And yes, you can actually remove quite large parts of the network, particularly if you do some scheme where you remove only every other layer or similar, or you have some metric to say how important any layer is. And that's actually a really simple but effective way of removing large parts of the computation. It's also nice that it sort of removes it in a serial way, right? So you, as much as you might be parallel across tokens here, you're always going to be serial in the depth of the network, and so you reduce some of the serial thing. I guess that's complementary to what I'm suggesting with these methods, right? So I'm sort of saying, let's reduce the dimension of the hidden state of the neural network. So all of your messages that are passed between layers are lower dimensional, and it seems very plausible that we could do both at the same time.
Okay, so I just have a few announcements just to finish with. Firstly, if you don't have to run off, we still have access to the room, the sort of breakout room, and there'll be tea and coffee available. And so do stay around, particularly if you want to ask James or Rita any further questions. Before you go, if you could remember just to hand in your name badges onto the sort of registration desk. And then finally, a lot of work went into putting this together, particularly by the Newton Gateway, so Claire and Svein on the registration desk. So do pass on your thanks to them before you go if you can. And with that, if we just thank all the speakers for today.
Thank you.